Hello, I'm Andrew Hirsch. I'm a postdoc at the Max Planck Institute for Software Systems, and I want to tell you a bit about my work with Deepak Garg on higher order choreographic programming. That means we want to enable higher order programming along with deadlock-free concurrency, all without using session types. Let's begin by thinking about an example. Alice wants to buy 2 books from Bob. To do so, she sends the title of the first book over to Bob, who looks up the price of the book and sends it back to Alice. They then do the same thing for the second book. Finally, Alice has to decide whether she's willing to pay for the books. She does so using the function f, which is a parameter of the protocol. She calls f on x and y, and then sends the result over to Bob so that he knows whether she's buying the books. However, things can go wrong if Alice and Bob get out of sync. For instance, imagine that Bob decides that it would be more efficient to batch requests and look up the prices of both titles at once. Then, when Alice sends over the title Jane Eyre, Bob will wait for the second title before sending anything back. But Alice won't send the second title until she gets the price for the first. Thus, Alice and Bob are in deadlock. We also have to think more about the function f that Alice uses to decide if she's willing to pay for the books. We already decided that f is a parameter of the protocol, but what can f actually do? Well, it could be very simple. Perhaps Alice just checks if x plus y is within her budget. However, maybe it's more complicated. Maybe one of the books, say Ulysses, is actually for Kathy. So in f, Alice needs to send the price of Ulysses, y, over to Kathy. Kathy then decides whether y is within her budget and sends that decision back to Alice, who calls it c. Alice then returns c and whether x is within her budget. Importantly, this means that f can itself contain communication. This is important, since it lets us reuse the basic code for Alice and Bob, whether or not Kathy is involved. Thus, we want a way to write concurrent and distributed programs, which guarantees deadlock freedom and can handle multiple parties. Moreover, we want that solution to be higher order so that we can pass a function which contains communication as a parameter to the protocol. Previous works have tried to provide these solutions, but none have quite fit this domain. In order to use session types, we'd have to use multi-party session types, which are very difficult to understand. Moreover, we would still need to write each party's program separately, increasing the probability that we get hard-to-debug type errors. Choreographies try to fix this by writing every party's program together as one big program. However, until now, choreographies have lacked any story for higher-order functional programming. We solve this by presenting Pirouette, which is a choreographic lambda calculus. Pirouette's design is parameterized on a local language of messages, which allow computation within a single location. It lists any type system for that local language to a type system for the entire language. And it has endpoint projections, which allows to compile Pirouette programs to one program per location. Our main theorem tells us that endpoint projected code is always deadlock free. Importantly, this guarantee only relies on simple types. Finally, all of our results are verified in Coq. To learn more about how Pirouette works, I hope you check out our longer talk and have a look at the paper. Have a wonderful Popple 2022.